Hi everybody. So in this video we're going to talk about the definition of a mineral. What is a mineral? And where we're going to start out is back in the 16th and 17th century. Early scientists had a very simple view, not necessarily a bad one, but they divided up the entire universe into three kingdoms: animal, vegetable, and mineral. So in their early classification scheme, they divided up the world into things that were alive, and those things that were alive and could move under their own power, that were animate, were called animals. Things that were alive and could not move, those were vegetables. But then look at this. Everything else in the entire universe, everything that wasn't alive, was considered a mineral. So, to scientists back in the 17th and even into the 18th and early 19th centuries, the mineral kingdom was literally everything that was not organic. So, air, water, all of the any liquids that would occur on Earth's surface, all solid objects. This was all part of the mineral kingdom, so it was very broad. Today's view of minerals is much more restrictive. We'll start with a key part of the definition. Minerals are things that are naturally occurring. Now, this doesn't change much from what scientists were thinking about back in the 18th century or the 17th century. Everything here was also naturally occurring. But it's really kind of a more important definition nowadays because in fields of engineering, there are so many artificial crystals that are being made. So if you, we'll just take a more familiar example. Let's take the element carbon. If you take a pencil lead that is made of graphite, that graphite may well be natural, but let's say you take the graphite into your garage, let's say you happen to have a 50-ton press, and you put the entire weight of that press onto this graphite material, you might create something that looks a lot like diamond. And it will have all the physical properties of diamond. It'll be one of the hardest known naturally occurring substances. It'll have the same atomic arrangement. It'll refract light in the same way. But it's not truly diamond because we made it. We would not call it a mineral because it's not naturally occurring. We might call it an artificial diamond rather than just simply diamond. So when we say the word diamond, we always mean something that has been found in nature. Now, another part of the definition is that minerals have a fixed composition. And what that really means is that we can write a formula. So we've written a formula here. Carbon is the formula for diamond. We can write something a little bit more complex. So the formula SiO2 is the formula for the mineral quartz. And you can really think of fixed composition as being equivalent to a recipe. How do we make something? Or not necessarily how we make it, but how would nature make it? So if nature is going to make quartz, you'll need 2 parts oxygen to 1 part silicon. If you have those elements in any other ratios, then you're not going to be able to make quartz, or you'll have material left over. If you want to make diamond, then you need carbon and nothing else. Pure diamond should be pure carbon. So when we say that minerals have fixed composition, what we mean is we can write a formula for them. A third part of the definition is that minerals have an ordered atomic arrangement. Ordered atomic arrangement. And so that means that the atoms that occur have some repeatable pattern. And I'm just going to draw atoms, these little dots here, as a cube because it's easier for me to draw than, say, the structure of quartz or diamond, where the structures, the patterns are a lot more complex beyond my limited drawing capabilities. Let me just draw a couple of cubes here. So when we say that minerals have an ordered atomic arrangement, we mean that those atoms come in a pattern. So, for example, if we have the mineral diamond or quartz, there's going to be a different kind of pattern. It's not necessarily going to be a cube, but it would be something that we could draw like that, where in 3 dimensions it's going to be highly repeatable. A fourth part of the definition is that the compositions of the mineral are homogeneous. So what that means is that if we've got the mineral quartz, or any other kind of mineral, well, actually, let's use a different example. Let's say we have something like sodium chloride. I'm going to use that example because sodium chloride actually has a cubic structure. If we have let's say we take these 3 little cubes and we link them together and make a large sodium chloride crystal. The mineral name is halite. Then it doesn't matter whether we analyze the mineral here or there or there. We'll always get the same composition. It will always be 1 part sodium to 1 part chlorine. And so if we have that, then we'll have the mineral halite. Same thing for quartz. If you have a quartz crystal, it doesn't matter whether you analyze the quartz near its tip or somewhere near its center. If you analyze it there or somewhere else, you'll always get the same composition. So the mineral should be homogeneous. So numbers 2 and 4 are rather closely linked. So to sum up this there's one last thing we should probably address. We started out thinking about how the early scientists classified materials, and minerals were everything that was not organic. You'll notice that we've left that out of our definition here. And the reason for that, a lot of modern textbooks are going to leave out the term inorganic as part of the definition of a mineral, is because there are minerals that are biogenic. And we don't necessarily want to leave these out. A classic example would be the mineral apatite, and that would be the mineral that your teeth are made out of. And for a lot of the scientific problems that mineralogists are working on, it really doesn't matter whether, let's say, apatite was formed by inorganic or biologic processes. We're still trying to address the same kinds of questions. We're interested in the same kinds of scientific problems. We're using the same kind of analytical techniques. So in recent decades, we've found that it's really not very important to say that something is organic or inorganic. So we'll talk about minerals, and sometimes we'll qualify them by saying that they are biogenic minerals if we think they were made by a biological process. And so for our definition, it doesn't really matter whether it's organic or inorganic. The only thing that matters is that the things that we're looking at are naturally occurring of a fixed composition. Those compositions should be homogeneous, and that there should be some kind of ordered atomic arrangement.